All right, yesterday we learned two new things. One that was relatively small and took us only a little bit of time. The other one that we spent the rest of class on, and we'll spend quite a bit more time on over the next couple of days. First one was finding the instantaneous velocity on a curved line graph. Listen, if we have a straight line graph, it looks like this, position versus time, and you want to find the instantaneous velocity at this moment in time, it's easy. Because if you've found the average velocity for the entire trip, the instantaneous velocity here, or here, or here, or here, or here will be exactly the same as the average velocity of the entire trip. You don't need to find anything special for the instantaneous velocity at any moment in time if it's a straight line. But if you got something like this, you do have to do something special. Okay, if you've got something like this, you can't just find a slope of the line and then say, oh, the velocity is the same everywhere, because it's not. It's different everywhere. It's increasing as you go through it. It's accelerating. So how do we do that? Let's say that I wanted to find the velocity at, let's make it 6 seconds today. Yesterday, I think we went on this graph 4 and 7. At 6 seconds, how do I find the velocity at that moment in time? Do I just go, oh, position 3 divided by time 6? Is that right? Well, the way that I set that up, probably not. It's probably more complicated than that. What are we going to do? Draw a tangent line. Let's draw a tangent line. And a tangent line, remember, is a line that goes A through only that one point. This goes through only that one point, but that doesn't work. This doesn't work. This doesn't work. It has to go through only that one point, but it also has to follow the curve. So a good tangent line might look something like this. Oh, that's not even great, because it kind of doesn't go through that point. Let's try that again. Well, you'd be using a ruler here, right? That's pretty good. What do we do with that tangent line once we've got it? 3 words. Find the... Oh my goodness, you guys. I think it's 8:30 on a Monday morning here with the way you guys are responding. Find a what? Find the slope. Yeah, find the slope. So let's pick 2 points on the line, preferably far apart. Hey, look, this one's perfect because it's right on the intersection of 2 lines, although it doesn't have to be. Okay, this one down here looks pretty good as well. In this case, we'd say the slope is equal to the rise over the run. The rise here is 5, right? 5 minus 0. The run is from 2 to 9, which is 7. So 5 over 7 gives me, I'm not sure what that works out to be. All I know is it isn't 0.5, which is what I had when I did it the other way. Right? 0.5 is what I got when I took a look at the y coordinate and the x coordinate. But remember, it's always based on change. So you can't just look at one coordinate and divide the 2. Okay, you got it? Well, the next thing we did was took a look at acceleration. This was certainly the bigger focus of yesterday's class, and it will be today's class as well. Acceleration we define as the rate of change of velocity. How quickly the velocity is changing. Not how fast something's moving, but how quickly the velocity is changing. Something can have an incredibly high rate of acceleration, but yet be moving very, very slow. Something can have an incredibly low rate of acceleration, but be moving very, very fast. The velocity is not related to acceleration. The change in velocity is related to acceleration. So, we learned yesterday that there was one main equation that described velocity, or acceleration, I should say. A is equal to delta V over delta T. Change in velocity over change in time. But we also learned there was 4 more that we could use anytime we had acceleration as well. Doesn't matter what order. I don't even remember what order I gave them to you yesterday. VIT plus 1/2 AT squared. What does delta D stand for there? Ryan, what does delta D stand for there? Good, good. What does VI stand for there? Initial velocity, good. What does A stand for there? Good, acceleration. Let's come up with another one that looks almost the same. VFT plus 1/2 AT squared. What does VF stand for in this case? What's VF? Jordan? Sorry? Speed? No. Oh, well, we're gonna let him fix it here. What is it? Velocity final, right? Final velocity. All right, let's go. D is equal to VI plus VF. Somebody yesterday, as they were going through a problem, said D is equal to VF minus VI. VF minus VI, we use a lot. It's delta V, the change in velocity, but not in that equation. It's VI plus VF times T. And then finally, we've got VF squared is equal to VI squared plus 2AD. What does VF stand for in this equation? Good, final speed, not final velocity, final speed. So all the other equations have vectors in them. This one does as well in A and D, but not with the speed, not with the initial and the final speed, okay? We're not going to get the direction of it when we solve that, just the magnitude. All right, yesterday I left you with a couple of problems on page 48. Okay, we had also taken a look at the problems on page 47. I think we had done one of those in class, but hadn't done the other one. Is there anybody that needs the other one gone over here from the first set that I gave you yesterday? Okay, gave you the second set. Anybody that needs either of these questions gone over from the second set? Number, both of them? Okay. Okay, let's take a look at both of them. You guys have all had a chance to read these. Question number 1 says, a hound running at a velocity of 16 meters south slows down uniformly. Slows down right there. Okay, right there. It's telling me what? Slows down. It's a group A or a group B problem? It's group B, right? It's slowing down. It's accelerating, or more specifically, decelerating. So it's a group B problem. I can use any of those group B equations, any of those equations that involve acceleration. It slows down to 4 meters per second in 4 seconds. What's the displacement of the hound during this time? Let's go a little bit different this time. Let's go south as positive. Usually we go north as positive, right? Why do I want to go south this time as positive? Yep. Right. Since it's the only direction, we might as well make it positive so that it's a little bit easier to do the math. What do we got here? 16 meters per second to the south. We've got 4 meters per second to the south. And then we've got 4 seconds. Tell me what this is, first of all. This is the easy one. Yep. Delta T. Good. Derek, what's this one here that's 16? Good. VI. And 4 meters per second would be, Haley, what? Good. Final velocity, VF. And we're looking for, I was going to say A. We're looking for displacement here. All right. We have 5 equations that we're allowed to use. We have 1 that we're not allowed to use. Okay? We can use any of these ones that are circled in blue, our group B equations. We cannot use D over T. Equation 1, my group A equation is valid only when we have constant velocity, and that's not what we have here. Which of those equations seems to fit the best? You don't have them in front of you right now? Pull out your data sheet. It's got them all on it. Which one seems to fit the best, Lewis? Okay, good. Let's try VI plus VF over 2 times T. We're in meters per second. That's good because that's where we need to be. VI is 16 plus 4 divided by 2 times the time of 4 seconds. 20, 10 times 4 is 40 meters. We got a positive 40. What does that mean? What does that positive 40 mean? It means to the south, because we define south as positive in this question, right, Stephanie? Oh, good question. Wouldn't the 4 be negative because it's slowing down? Good question. Would it be negative because it's slowing down? Would the time be negative because it's slowing down? No. Oh, VF you mean? VF, okay, okay. Would VF be negative because it's slowing down, guys? No. What is negative because it's slowing down? Well, if it was going in a different direction, we'd make it -4 for sure. Yeah, yeah. What becomes negative, though, just because something's slowing down? The acceleration. Okay. The velocity direction, the positive or negative on velocity, depends only upon which way it's moving. So 16 to the south, well, we made south positive, so that's going to be positive. 4 to the south, okay, we made south positive, so it's going to be positive. It doesn't matter that it's slowing down. If it was speeding up, wouldn't matter either. Okay, the only thing that it matters in terms of negative, positive, when it's slowing down, is the acceleration. Okay, does that make sense? Guys, questions like that are good questions. Okay, we've got to resolve those questions now. That's why we did 4 of these questions yesterday. That's why we're doing more of them today, is to fix those little things that are going on inside our head that aren't quite right. Okay? We're all going to have issues like that. Ask those questions. Ask those questions. Get them corrected now so that we don't make those mistakes come quiz time or come test time. Okay, number 2. So the ball moves up a hill with an initial velocity of 3 meters per second. 4 seconds later, it's moving down the hill at 9 meters per second. What's the displacement of the ball? Well, in number 2, let's define up the hill as positive. What do we got given to us then? What do we got given to us? Oh, we have a time. Good. What's the time? Good. We'll make it 4.0 seconds. All right, what else do we have given to us? Well, this one thing. Okay, give me one of them. VI. What's VI? Positive 3 meters per second. Good. You told me you have VF. Who else can tell me what VF is? Good. -9. Now, Stephanie, I'm glad you asked that question on the last one, right? Why is this one -9 for VF? Good. It doesn't matter whether it's speeding up or slowing down. In fact, it's actually speeding up, right? It slows down, it stops, and then it goes in the opposite direction, ends up moving faster than it started at. It doesn't matter whether it's speeding up or slowing down for VF. What matters is that it's going down the hill. We're looking for the displacement again, delta D. Which equation do you want to try for this? Group A or Group B, by the way? Constant velocity or acceleration? Brian, you weren't here yesterday, but I'm going to ask you, is this involve constant velocity, or does this involve speeding up or slowing down? Good, good. Whenever we have acceleration, we're allowed to use those 5 equations that were circled in blue on the last page. Which one do you want to try here? Which one do you want to try? Yeah, the same equation that we just used for the last question. VI plus VF over 2 times T. Now VI, this is a little bit harder mathematically. VI is 3 plus -9 divided by 2 has a time of 4 seconds. 3 plus -9 is -6, divided by 2 is -3, times 4 is -12. And lo and behold, we just got the answer that they gave us in the book here. -12 means down the hill, by the way. So it was going up the hill, it stopped, and then it started going down the hill. It ended up 12 meters down, further down the hill than it started. All right? Carrie, is this okay? As I was walking around, guys, checking to see who's done these, I saw a couple people using this equation for one or both of these questions. Why can you not use that equation? Why can you not use that one, Carrie? Right, it's not constant velocity. Okay. The only exception to that is that if you were asked for the average velocity, then you could use that actually, but that's not very common. All right, let's do another one. We do lots of these problems, guys, because this is so important for everything we do in Physics 20 and Physics 30, this whole acceleration thing. I'll give you a chance to read this, take 30 seconds, and then we'll see if there's anything you need help with. And we'll go over it as a class. Any crazy words there? Probably not. That is, if we understand what acceleration means and displacement means, there's no crazy words. Okay, if we're still struggling with what those things mean, then yeah, this is a really hard question. Golf ball that is initially traveling at 25 meters per second. That makes VI 25 meters per second. We don't know which direction, right? North, south, east, west, we don't know. Let's make it the positive direction. It's going 25 meters per second, the positive direction, whatever that means, whatever that is. Slows down with an acceleration of -20. Oh, they give me a break here. If it was me writing this question, I would have said it slows down at 20 meters per second squared. You would have had to recognize that it was -20, not just 20. Okay? Why should you know that it's negative even if they didn't tell you that? Yep. It's slowing down, right? It's slowing down. Now, it's confusing, right? We just finished saying on the last page here that it wasn't negative because it was slowing down. Two different things. The velocity is negative because of its direction, not because it's slowing down. The acceleration is negative when it's slowing down. Is that all we have? No, we got 2 seconds. This is my time here. And we want to find the displacement here. Is it group A or group B? Tony, group A or group B here? Constant velocity or acceleration? Group B, yeah. We've got 5 equations. If you're not sure which one to pick, just pick one. Guess one. Try it. See if it works. If it doesn't, try again. Which one do you want to try first? Which one seems maybe to make sense to try first? Okay, A is equal to delta V divided by delta T. If we do that, we've got A, we've got T, we've got VI, we don't have VF. So we could solve for VF there. Yeah, so we want to find displacement. That's not going to get us displacement, right? But that's okay. We could get delta V, then we could get VF from delta V, and then we could maybe use that in some other equation. So it's not the most efficient way of doing it, but it would work. Is there a way to do this that's a little bit quicker, a little bit more efficient? Zane? Which one was that? VIT plus 1 FAT squared? Okay, let's give that a try. And let's see if we have everything we need there. D, looking for it. VI, T, A, T. Looks good. Okay, let's give that a try here. VI is 25 times 2. Oh, be careful here. Be careful. -20. 25 times 2 is 50. Subtract. Subtract. Where does that negative come from, guys? Yep, Lana? Yeah, it's 50 subtract whatever because it was plus a negative number up here, right? What is this on the right-hand side here? A half times -20 times 2 squared. 2 squared is 4. 4 times 20. 4 times 20 is 80 times a half is 40. 50 minus 40 is 10 meters. So 2 things here to watch out for. Don't miss this -20, which means you end up subtracting the right-hand side because you're adding a negative number. But also don't forget that square. Okay, that is, both of those are really, really common mistakes in this equation. Miss the negative, forget the square. Right? 2 questions on page 50. Let's see what you can do. Okay, everyone, we're having a look at question number 2 here. It says, a motorcycle traveling at 100 kilometers per hour. Right away, you know what I want to do? Okay. I want to circle that or draw attention to that somehow, because that's non-standard units. I want to be in meters per second, not kilometers per hour. Go get yourself tonight an ugly colored highlighter. Go to the ugly highlighter store and buy yourself the ugliest highlighter you can find, the ugliest colored highlighter you can find. And every time you see something like this, kilometers per hour, that you know you're going to have to convert, highlight it. Draw attention to it. Okay? Somehow draw attention to it, whether it's circling it red, highlighting it, an ugly highlighter, whatever, it doesn't matter. Draw attention to it to remind you that you need to do that conversion. Applies the brakes, 0.80 meters per second. I'm actually going to do something here in red as well to draw attention. Negative, right? It's slowing down. The velocity won't necessarily be negative, but the acceleration will be because it's slowing down. Time of 1 minute. How far did the motorcycle go? VI is 100 kilometers per hour. That's what it was moving. Not through the whole trip, but at the beginning of the trip. 100 kilometers per hour. That's 100 times 1,000 meters divided by, well, there's 3,600 seconds in an hour. That ends up being equal to 27.777, I believe, meters per second. My acceleration here is negative 0.80 meters per second squared. In my time, oh, okay, I almost missed something. Get out that ugly highlighter. My time is 60 seconds. You got to convert that as well. How far did it go? Looking for displacement here. We're going to use the same equation, I think, as we used in the last one. V is equal to VIT plus 1/2 AT squared. VI is 27.7778 times 60. Negative 0.80 times a time of 60 seconds. Okay, follow along on the calculator. We'll do this one as a group here, okay? Let's say 27.7777 times 60. Okay, that's the number, the first number, 1666.666. Double number right there almost, eh? Like all these sixes. Worse than 666 because the sixes are everywhere here. Guess what? That's why you guys hated this question so much, right? Because the devil's embedded in the question. 0.5 times negative 0.8 times 60 squared equals negative 1440. So it's 1666 plus negative 1440. Or you could just say 1666 subtract 1440. Subtract 1440 now. What did I do? What have I done? Oh my goodness, what have I done? Yeah, I just subtracted a negative. I didn't want to subtract the negative. I wanted to add the negative, right? So it's 1666 subtract 1440, not subtract negative 1440. 226. Now, lots of people got that and said, wait a sec, that's not the answer they have here. Yes, it is. 2.3 times 10 to the 2. You guys know scientific notation. Put that in scientific notation. 2.26 times 10 to the 2. Well, they just rounded it, that's all. 2.3 times 10 to the 2, 2.26 times 10 to the 2, whatever. Okay. Their answer is based on significant figures, and some of you guys know about that, some of you guys don't. We're going to focus on that a little bit more after our first unit test. Okay. So don't panic about that right now. Good? Okay, I'm getting lots of questions from people. That's good. Okay, that's good because it's developing a better understanding for you about these questions. And I think you guys are getting this. But we're going to do another one here. Page 51. So it says a speedboat slows down at a rate of 5 meters per second squared. wait a sec, slows down, negative, right? Ugly highlighter time. Comes to a stop. The process took 1.5 seconds to find the displacement of the load. A, negative 5.0 meters per second squared. Time, 15 seconds. Displacement. Anything else we have? If we read between the lines, okay? Good, good. Reading between the lines, VF has got to be 0 because it says it comes to a stop. Final velocity is 0 when it comes to a stop. Is this group A or group B? Constant velocity, or is this acceleration? Acceleration includes deceleration, by the way, as well, right? George, is your hand up there? It's group B. It's acceleration, right? Which one of those group B equations do you want to try first? How about this one? A is equal to VI plus VF over 2 times T. That's good, right? Is that a valid equation? Absolutely. Problem with it is, I don't know what VI is. Right? Don't know what VI is. So that's not going to really help me there. Lewis? Okay. So D is equal to VFT minus 1/2 AT squared. Let's see if this one works. D, we're looking for it. VF, got it. T, got it. A, got it. Works for me. Okay, let's plug our numbers in. VF is 0 times 15. Subtract 1/2 of negative 5 times 15 squared. This is just 0, right? 15 squared is 225. 225 times 5 is 1125. 1125 divided by 2 would be 562.5. Somebody check that. Is that right? Negative, right? I was subtracting 1/2 of negative 5, so negative 562.5. What is that? 0 minus negative 562.5. Right, positive 562.5. Now, it should be a positive number, right? If the boat is moving in the forward direction, then its displacement must be in the forward direction. Its displacement must be a positive value here. By the way, we should really round this to 2 digits. If you look back to your data, 2 digits, 2 digits, final answer should be 2 digits. We're going to say 5.6 times 10 to the 2 meters with that one. I wouldn't mark this wrong, but this is slightly more correct. Yep. I'm sorry? Who did? Yeah, he's right. You should round at the very end. We're at the end of the question, right? So like right here, I got 562.5. I'm not going to round that to 5. I'm not going to round that to 5.6 times 10 to the 2 because that's not a final answer. Okay. But when I get down here, it is a final answer, so now I'll round it. Okay. No, he's absolutely right. Don't round until you get to the end, but when you get to the end, that's when you round it to 2 or 3 or 4 digits, whatever. Okay, again, we're not going to lose any sleep over that. If you're puzzled by the whole significant figure thing, don't worry about it right now. Okay, don't worry about it. Okay, worry about acceleration right now. We'll get to that. But if it's kind of making sense, then see what you can do with it. Okay, try these ones. Page 51. Okay, let's take a look at the first one here. If the arresting device on an aircraft carrier, sometimes our problem is, as much as we might not realize it, it's just the wording of something. Like a term that doesn't make sense. I always give you a chance to read a question first, right? And then we go over a question. Well, you've read this. Okay? Ask me if there's a word that doesn't make sense. The arresting device on an aircraft carrier? What is that? So this is the ocean, and this is my aircraft carrier right here. Okay, the plane comes down here. Let's not put wheels on it. I'll butcher it if I try to do that. I guess we need wheels to land, don't we? The plane's coming down to land on this aircraft carrier. What are you laughing at? You don't like that airplane? Would you like to draw a better airplane, huh? Would you like to do that? How many people like my airplane? Thank you. Thank you. I like all of you that just had your hand up. So the airplane's coming down here, and it lands. Guys, this runway on this aircraft carrier is not very long. I've been on an aircraft carrier. It's not very long. It's not very long at all. Somewhere down here, they actually have this steel cable that goes right across the runway. Why do they have that? Well, because this airplane has this little hook hanging out the back of it. The airplane, when it's coming down, believe it or not, actually, as the airplane's approaching to land, it does not put on reverse thrusters like an airplane when it lands at the Calgary airport. It doesn't try to slow down like at the Calgary airport. Okay, you guys know, you guys have flown before, those of you who have flown before, when you're landing, as soon as you hit the ground, what happens? The reverse thrusters go on and you slow down like crazy by those reverse thrusters, right? Doesn't happen on this aircraft carrier. As this plane comes down, you know what it does? The pilot guns it. The pilot puts the jets on to go faster. Why would you want to go faster as you're landing on this aircraft carrier? In case you miss. If you're going too slow and you miss, what happens? You crash into the ocean, right? If you're going faster and you miss, what happens? You go back up. So if you miss landing, you just go right back up. As soon as you get over here, as soon as this plane comes down here and that little hook catches on that steel cable, as soon as it catches, that's when the reverse thrusters go. This arresting device stops the airplane like almost instantly. It's crazy, the rate of deceleration of this, okay? 15 meters per second squared. In fact, I would suggest it's probably even a higher rate of deceleration actually in real than 15 meters per second squared. It slows down very, very quickly because this hook grabs a cable. And it grabs the cable because we have to gun it in order to, just in case we miss the runway. Well, if we gun it, then we're not going to be able to stop on our own, right? So we're going to have something to help us. As soon as the pilot knows that he's caught the cable or she has caught the cable, then that's when they put the brakes on. Okay? But this is the big thing. Okay, this is what stops us. This is what gives us the big deceleration. This arresting device on the aircraft carrier. All right. So it stops it in 150 meters. My displacement would be 150 meters here. The acceleration is -15. It's slowing down at 15 meters per second squared. Okay, again, I would suggest that the acceleration is going to be probably quite a bit higher than that. The time that it takes the plane to stop, delta t. That's what we're looking for. Anything else that we have given to us here? Right? Good. So VF would be 0 meters per second, right? Anything else? I think that's it. Ooh, I think this is going to mean rearranging something, isn't it? Which equation do you want to use? Forget about rearranging right now. Which equation seems to fit the best? Let's try this one. Oh my goodness, this is the first time we've really had to do serious algebra this year. df is 0, so 0 times time is 0, right? Let's cross that off. We want to get t here. Okay, follow along very, very carefully. Okay, this is tricky. You got to get rid of the half. You got to get rid of the a. You got to get rid of the squared. Let's get rid of the half first. We're dividing by 2 there. Let's get rid of it by multiplying by 2. Just get rid of the half. Divide it by 2, multiply the other side by 2. Now I got to get rid of the a. What do I do? What do I do with a on the right-hand side? On the right side, it's multiplied. How do I get rid of it? Divide it. So it becomes 2d over a equals t squared. Hold on one second here, guys. Now, finally, got to get rid of the squared. How do I do it? Square root. So it becomes 2d over a square root equals t. Now it's not so bad. Okay, plug in your numbers, solve for the time. Should work out to be 4.5 seconds. All right. Here's your homework, guys. Here's your homework. There's some check and reflect questions on page 53. There are 14 of them. The good news is I'm going to have you do tonight 6 of them. Okay, so your homework is page 53, number 1 to 6. Got it? All right, that's it for today.